Good morning, students. Today we will start a new chapter called Beginning of Modern Physics. So whatever you learned in grade 11 before and also in grade 12 so far is not modern physics. They are old physics. We sometimes call it classical physics or Newtonian physics. Now we are going to learn modern physics. Can you guess from which year this modern physics must have begun? Can you guess in which year? Starting from which year we call it modern? Any
20th
guess?
After
century.
Newton,
20th century, that is right. 20th century is right. Someone told about Newton, right? Newton's physics is called classical physics or old
after
physics.
Newton, I said.
Yeah, after Newton. Yes, after Newton is also right. So it's in the beginning of the 20th century or 1900s. The modern physics begins in 1900. Now let us see what is the concept of modern physics and who put forward this new concept of modern physics. So by the end of the 19th century, scientists thought that all the physical phenomena observed till then is completely explained with the laws of physics that existed by that time. So with the Newton's laws of motion, Newton's law of gravitation, then Maxwell combined electricity and magnetism. Now you have learned electromagnetic induction and all, right? So with all these ideas, the scientists thought that physics has come to an end. Almost all the phenomena that we observe in the physical world can be explained with the laws that existed till then. Then came two revolutionary ideas, which was completely unacceptable with the common sense point of view that existed till then. And those two revolutionary ideas were put forward by Max Planck and Albert Einstein. Have you seen Max Planck before? I, I know that all
We,
of,
We
yes,
heard, not
you
seen, I
have
think.
we
heard.
heard teacher.
Yeah, but I think all of you will be familiar with Albert Einstein's picture, right? You
Yeah,
are
yeah.
familiar
Of
with
course, I'm
Albert
facing
Einstein.
his dream.
Yeah, and maybe this phase is new to you, but you can see that he is the father of quantum physics, which is a revolutionary idea he put forward in 1900, and it started the era of modern physics. So in 1900, Max Planck invented quantum theory, which revolutionized the world of physics, and he is known as the father of quantum physics. Can you imagine that some bodies can give out energy? You know, electromagnetic radiation, light, and all, which we learned are waves, right? Waves means continuous thing. So we also expect naturally that energy can have any value. But he put forward the revolutionary idea that energy cannot have any discrete value. Energy can have any continuous value, any value. He thought that energy can have only particular values. So it was an idea which was not easily accepted by the world of physics then, but his idea was necessary to explain many of the physical phenomena which was found later. So Max Planck put forward the quantum theory and the theory of radiations, black body radiations, which was totally new to the world of physics. It was totally new to the concept of physics which existed till then. Then in 1905, that is 1905, Albert Einstein, he was only 26 years old then. He put forward the concepts of relativity of time, mass, and space. It further revolutionized physics. Can you think of a case when a body is moving very fast and its mass changes? Will the mass of a body change with its motion?
Yes, teacher.
You know it changes with motion because you have learned something about that before, right? But in the beginning of the 20th century, that was an idea which could not be easily digested by the scientists. So the idea of relativity of time, mass, and space was put forward by Albert Einstein in 1905, and this further revolutionized physics. So these two revolutionary discoveries or inventions, we can call them, gave the concept of modern physics, totally different from the classical physics which existed till then. Now, what are the branches of modern physics? The different branches of modern physics are quantum physics, started by Max Planck, and the relativity, which was by Albert Einstein, then atomic physics, nuclear physics, statistical mechanics, and solid state physics. Now, look at this point. Atomic physics, nuclear physics, solid state physics, this all go deep into the structure of matter. It goes to the microscopic level. Now, classical physics still holds whenever we are discussing the physics of large objects, or we are discussing physics of objects which are moving with a speed not comparable to that of light, then all the laws of classical physics still holds. But when we go to very tiny particles, microscopic particles, and also whether when the particles are moving at very high speed comparable to that of light, the laws in classical physics are not applicable. There we need a new branch of physics called relativistic physics. So this is the idea. Classical physics is still good. Don't think what you have learned so far was of no use. It's still useful because we are still surrounded by macroscopic particles, cars, train, helicopter, all their motion needs classical physics. But when we go deep into particles, which are very tiny, we need a new area of physics, which we call the modern physics. That is why the atomic physics, nuclear physics, all comes under modern physics. So, before going into the concepts of modern physics, let us clarify a few ideas. What is meant by a frame of reference? Okay, if you want to tell the position of an object, how will you tell the position of an object? You must have learned in math how to tell the position of an
Yes,
object.
teacher. X, Y, and Z, right?
Yeah, we use the Cartesian coordinate system, that is x,
Yes.
y, and z axis. So if we tell three coordinates, we can say that it has it's positioned at this place. Now, a frame of reference is nothing but a coordinate system in three-dimensional space with respect to which the motion of an object is described. What is meant by motion? Motion means the change of position, right? So whatever coordinate system which we use in three-dimensional space with respect to which we can tell the position and the change in position, that is motion of an object, we call it a frame of reference. Now, the concept of motion and rest itself depends on the frame of reference. For example, suppose Irfan is standing in a railway station. Have you ever been to a railway station, Irfan?
No, teacher.
Because you are here in Bahrain. Is there anyone in the class who have been to a railway station?
Yes, teacher. Aye.
Yeah, you went to Bangladesh and there
Yeah,
you,
yeah.
yeah, okay.
I
So
traveled through.
forget about Irfan. Let us assume Muhammad Zaman is standing in the railway station. Okay. And you find someone else. Is there anyone else who have traveled in train before?
Abdul.
Yeah.
Maybe.
Abdul, Abdul is traveling in a train. So when Muhammad Zaman look at Abdul, Abdul is traveling in train, right? So he is moving with respect to Muhammad Zaman. Now at the same time, Muhammad Zaman is looking at a tree opposite to the platform. Is it moving with respect to Muhammad Zaman?
No.
No, it is at rest. But when Abdul looks at Muhammad Zaman and the tree, are they moving?
Yes.
Yes, because now the frame of reference we have shifted from Muhammad Zaman to Abdul. So the concept of rest and motion depends upon the frame of reference with which we are observing that. Now, frame of
Teacher,
reference, yes.
are you explaining relative motion?
Yeah, we are going to that region. We are going to it.
Okay.
So, these frames of reference itself can be classified into two types: inertial frames of reference and non-inertial frames of reference. Here, what is meant by inertial frame of reference? Suppose you have two frames of reference. As example, let me consider this O frame of reference is attached to Mohammad Zaman. He is standing on the railway platform. He have visualized his X, Y, and Z axis, and he can tell the position of a tree. Okay. Now the train in which Abdul is traveling, and it is traveling, suppose it is traveling with a constant velocity v, then, or if the train is at rest in the railway station, in those two cases we can call Muhammad Zaman's frame of reference and Abdul's frame of reference inertial frames. Inertial frames means frame of reference either at rest or moving with uniform velocity. So even if they are moving with uniform velocity, that is a constant velocity, we can call that inertial frames of reference. Now, inertial frames of reference are those frames in which Newton's laws are valid, which means all the classical laws of motion are valid in inertial frames. So, if you are considering two frames of reference which are at respect to each other, moving with a constant velocity or at rest, then we don't need a new frame of reference or new concept of relativity. It's fine. We can consider the Newton's laws applicable. Now, in inertial frame of reference, there will be zero acceleration. When the train is speeding up, if it is accelerating, we cannot call the frames of Muhammad Zaman and Abdul as inertial frames. So, if the frame of reference is accelerating, we cannot call it inertial. What is the connection between force and acceleration? Will there be a force on any accelerating body? Will there be a force? Yes, you have learned that force is equal to mass times acceleration. So whenever a body or a frame of reference is accelerating, there will be a force acting on it. So such frames of reference are not considered inertial. Now, the example is a train moving with uniform velocity. Now, another frame of reference is called non-inertial frames of reference. Frame of reference, which is either having a uniform linear acceleration or being rotated with uniform speed. Can you tell me why a frame of reference which is rotating with uniform speed is considered non-inertial. They are rotating with uniform speed.
So
They
what you
don't have
can
any acceleration.
Yeah, they are having acceleration. Yes, that's right. Why are they having acceleration? See, their speed is not changing. So why are they having acceleration?
their direction is changing, right?
Yeah, their direction of velocity is changing. Even if the magnitude of velocity, which is speed, is not changing, the direction of velocity is changing. So they have an acceleration. So rotating bodies or rotating frames of reference are non-inertial. And in non-inertial frames of reference, Newton's laws are not valid. So in rotational frames of reference, we can say that the Newton's laws of motion are not valid. And in non-inertial force, a zero force doesn't correspond, which means there will be an acceleration for the non-inertial frame and there will be a force acting on it. So what is an example for a non-inertial frame? A freely falling elevator may be considered as a non-inertial frame. Can you tell me another example for non-inertial frames of reference? Any other example? You know that an accelerating frame or a body which is moving in rotational motion is a non-inertial frame. So can you tell me an example for it?
Like if we rotate a ball, like if we connect a ball with a wire and we rotate the,
Yeah, so when you consider frame of reference which is attached to the ball, it is a non-inertial frame of reference. That's right. That's right. Then can you consider Earth as a inertial or a
Yes, teacher, I
non-inertial?
was going to say Earth.
Yeah,
Yeah,
Earth. Like, so when can we
it
consider
will take
Earth
care of
as
this.
an inertial frame and when as a non-inertial frame? Whenever we are looking at a phenomena or an event which is taking place on the surface of Earth, suppose I'm sitting in a chair and a ball is rolling in front of me. So both the ball and I am in the same frame of reference. So with respect to each other, if we consider Earth as a frame of reference, it is inertial, right? So when I observe the motion of ball with respect to Earth, I am at rest with respect to Earth, and Earth is also at rest with respect to me. So I can consider Earth as an inertial frame. But suppose I'm traveling in a spaceship and I have gone out of the gravitational field of Earth. Suppose I have gone out of the gravitational field of Earth. I'm no more rotating with Earth. So when I see Earth as a separate planet, I see that it's a rotating body. Now, if I want to make observation of a phenomenon which is going on just in front of me, I cannot consider Earth as an inertial frame of reference because it is accelerating, it is rotating. Is that clear to you? So
Yes, teacher.
Newton's laws of motion is still applicable when we are uh, stationed on the surface of Earth because the Earth is not moving with respect to us. So that is the case when it comes to practical things. Now let us see another new concept. Have you ever heard of Michaelson and Molly? Have you heard of this scientist?
No,
no,
teacher.
it's new for
Albert
us.
Michelson and Edward Molly. So these are
No.
two scientists who conducted an experiment. Do you know? To check what?
The Earth's gravitation?
not Earth's gravitation, but something related to the universe. Like during classical physics times, scientists believed that throughout the universe there is a medium which existed, and they call this medium ether. So it was considered as a medium which prevails throughout the universe. Now we know that electromagnetic waves does not require a medium to propagate. But in classical times, it was really difficult for the scientists to digest an idea that a wave can travel without a medium. Because whatever they have observed is the motion of wave on a string, the motion of sound waves. Like if you even keep some sand on a table and beat on them, the table vibrates and the sand vibrates. So they have always seen waves traveling through a medium only. So how the light from sun can reach us? There should be some medium in between. So that medium was an imaginary medium called ether. And since we can see the stars and all, which are far away, they thought the whole universe is filled up with this hypothetical medium called ether. And Michaelson and Molly in 1887, see, to the end of the 19th century, performed a famous experiment to determine the existence of ether. And from the experiment, they concluded that there is no such imaginary material called ether. So it's just a hypothesis. It doesn't exist. That was the conclusion they made after the experiment. And in the same experiment, they also found that the speed of light is a universal constant. Now, we all agree without a second thought that the speed of light in vacuum is a constant, right? And we know that value and we use it for many problems in physics. So they are the two scientists who conducted their famous experiment, which is called Michelson-Morley experiment. Now, this experiment and also another experiment conducted by a scientist called Millikan's oil drop experiment. These two experiments are considered unparalleled. They are considered classical experiment in terms of the accuracy and precision with which these experiments were conducted. It's really unparalleled. Never in physics such perfect experiments under the given circumstances are done. So still we think of and we learn these experiments conducted by Michelson and Morley. Now in the next class, we will be discussing in detail the Michelson-Morley experiment, and we will see the apparatus they used and also the mathematical derivation which they followed. Okay, so we will discuss tomorrow Michelson and Morley experiment in detail. Now let us see another concept which we will be discussing in this chapter, that is Einstein's theory of relativity. You have already learned a little bit about Einstein's theory of relativity, right? What do you know about that? What have you learned related to Einstein's
It's
theory of
related with
relativity?
time dilation, right?
Yeah, it's related to time dilation, yes. Then,
It's related to gravity.
there is something related to gravity, yes. Have you learned that in detail, how it is related to gravity? I don't think so.
The structure of gravity is like this, right?
Yeah, the field
That's the structure
curve.
of gravity. Yeah.
Equal to mc square, that one also, right, teacher?
E is equal to mc square. That is the mass energy relation. Yes. And then what else?
Then teacher, et equal to mc squares.
E is equal to mc square. Just like you told me, time dilation. That is correct. What about length?
No.
Length. length contraction, and also mass increase. So these are the changes happens when a body is in motion. So in this chapter, we will be learning in detail about time dilation, length contraction, mass increase, and also the mass energy relation. But we won't be learning much about the law of gravitation, whatever Mr. Einstein have put forward. So Einstein's theory of relativity, there are two. There are two theories of relativities. One is called the special theory of relativity, and the second one is called the general theory of relativity. In special theory of relativity, the laws of dynamics, that is the laws related to motion, and the relativistic concept of space, time, and mass, that is what I call length contraction, time dilation, and mass increase. And the conclusions deduced from these laws and concepts are known as special theory of relativity. In this chapter, we will be learning the special theory of relativity. While general theory of relativity refers to the general theory, he expressed the scientific and philosophical views regarding the motion of planets, stars, and comets, and gravity, and the structure and composition of this universe. So, we won't be focusing on the general theory of relativity, but we will be seeing in detail the special theory of relativity. So these are the concepts which we will learn in this chapter related to Einstein's theory. And again, we will learn about the fundamental forces in nature. Have you learned about fundamental forces in nature before? How many fundamental forces are there? You have learned about different types of forces, right?
So what type of force are you telling?
Like what all kinds of forces you have learned before?
Gravitational force,
Gravitational force,
magnetic force,
magnetic, then,
then one Lorentz force something.
yeah, that is electric and magnetic force
Yeah.
together.
And
So let me call it as electromagnetic force. So you have already mentioned two fundamental forces. One is gravitational force, the second one is electromagnetic force, and then
Frictional
hmm,
force.
frictional force is also a kind of electromagnetic force. We will see that. So frictional force is there, and then many kinds of spring force. You have learned about different kinds of force, but all these forces can be put in four fundamental forces. One is the gravitational force, then you have the electromagnetic force, then the nuclear force, strong nuclear force, and weak nuclear force. These are the four fundamental forces. So in this chapter, we will also learn about the four fundamental forces and an attempt by scientists to unify all these forces, all the laws in physics, which was not successful. And later, we will also see the different new concepts like photoelectric effect, Compton effect, and also the black body radiation. So all these concepts and X-rays. So all these are the topics which we are going to cover in this lesson. So this was just an introduction for the new lesson, beginning of modern physics. So